Okay, students, today we'll try to understand what is Fajan's rule. If you remember, while discussing dipole moment, we have seen that the covalent compounds have some kind of partial ionic character because of the difference in their electronegativity. Since none of the, I shouldn't say none of the, as most of the covalent compounds have partial ionic character, similarly, all ionic compounds have partial covalent character also. None of the ionic compounds are found to be 100% ionic. So, how to understand which one will be more covalent or which one will be less covalent? Fajan has given certain rules, a set of rules which help us to identify the covalent character of an ionic compound. Now, what is the cause of covalent nature in ionic compound? As you know, when the positive ion is coming, when the positive ion comes near a negative ion, they attract each other. But at the same time, you have to remember that negative ion means it has excess of electrons compared to number of protons. So when they come in front of a positive ion, the positive ion pulls the electron towards itself by causing the change in the shape of the anion. We call this term polarization or distortion of the electron cloud. Now, more is the distortion caused by the positive ion, more is the covalent character. The positive ions are said to have polarizing ability, and the negative ions, they get polarized, and the process is called polarization, which means they have more covalent character. You can see I have drawn a diagram here. In the diagram you can see I have put positive and negative ions. These are individual ions when they are not really very close to each other, and you can see their shapes are more or less perfect spheres. All right. My spheres are not really good. But when they come closer to each other, you can see the positive ion is causing a change in the shape of this negative ion. This negative ion is no longer symmetrically distributed. You can see here the shape is more, the electron clouds is more towards the positive ion and less towards the negative ion. So it has undergone kind of polarization, and hence it has developed some covalent character. Now, how to understand that? Let us go through the rules one by one. Rule 1. Smaller the cation, the rule says smaller the cation and bigger the anion, more is the covalent character. Now, how to understand this? For this, we have taken the example of sodium chloride and potassium chloride. This is sodium. It has electronic configuration 281, and when it forms a cation, it forms 28. Its electronic configuration is 28. So you can see it is occupying 2 shells. And chloride is 287, and it accepts an electron and forms electronic configuration 288, having 3 shells. And potassium is having electronic configuration 2881, and when it acquires a positive charge, by losing 1 electron, it has electronic configuration 288. That means it is having 3 shells. That means potassium is larger than sodium ion. Now, what does the rule say? The rule says smaller the cation and bigger the anion, more is the covalent character. Now, out of sodium ion and potassium ion, which one is bigger or which one is smaller rather? Now, you can see sodium ion is smaller than potassium ion. So, sodium will cause more polarization because it is very close to, its nucleus is very close to the neighboring atom. Okay, outermost shell of the neighboring atom. More is the size of the cation, its nucleus is far away from the outermost shell. As a result, its ability to pull electron from the neighboring atom becomes less. So here we find that potassium ion can cause more polarization, and hence potassium ion can cause, I shouldn't have written more here, it should be less. Please make a correction. It should be less polarizing, and sodium chloride is thus more covalent compared to potassium chloride. And you may notice here the chloride ion is common here, so the role of anion is not being played here. So here the explanation is only on the first point, that is smaller the cation. Now let's move to the next example. You can see here I have kept the same and we have changed the anion. You can see here we have taken sodium fluoride and sodium chloride. Now the rule says larger the anion, more will be the covalent character. Now out of fluoride and chloride, which one is larger? If we write the electronic configuration of fluoride, we find fluorine is 9 and its electronic configuration is 2,7. But when it forms fluoride, it gains 1 electron, it becomes 2,8,8. And chloride becomes fluoride is 2,8 and chloride is 2,8,8. So fluoride is having 2 shells and chlorine is having 3 shells. So definitely radius of chlorine will be more than radius of fluoride. Therefore, the nucleus of chloride is much far away from the outermost shell compared to fluoride. So which electrons can be pulled easily? The electrons of chloride can be pulled easily by sodium ion, causing more polarization. Hence, sodium chloride is more covalent than sodium fluoride. Now remember, during exam you may not be asked to write the definitions of the rules. You may be given a set of molecules from where you have to identify which one is more covalent in nature. Now let's move to the second rule. The second rule says the greater the charge on the cation, more is the covalent character. That means if I have different cations, one carry positive charge, one carries 2 positive charge, one carry 3 positive charge, say for example NaCl, MgCl2, AlCl3, where I have kept the anion same for our simplicity. So what happens here? You can see here that sodium chloride and magnesium chloride, I have taken the example and I have taken chloride, the same anion in both the cases, because our purpose is to learn the effect of charge. Now we know here sodium carry 1 positive charge and here magnesium carry 2 positive charges. Now magnesium having 2 positive charges means its ability to pull electron is stronger. So magnesium will pull electron from chloride more strongly than sodium ion. As a result, magnesium chloride is going to be more covalent than sodium chloride. I hope the rules are clear. And if I give you aluminium chloride, what is the charge on aluminium? Aluminium will have 3 positive charges. So aluminium chloride is going to be much more covalent. Rule 3 is slightly tricky. Here it says that if the size of the cation and the charge of the cation is also same, then what will happen? The charge is same, the size is also same. In that case, how to decide? Now you have to check the element belongs to which group. If the metal belongs to S block or even P block, and if the other element belongs to D block, then the one which belongs to D block will have more polarizing power and make the molecule more covalent. We are just taking a hypothetical situation of magnesium chloride and FeCl2 ferrous chloride. I'm not very sure because we don't have the data here about the size of the magnesium ion and ferrous ion. I'm just assuming that magnesium ion and ferrous ion, they carry same charge, +2, +2 you can see here, and I assume that their sizes are same. Alright, I've just assumed. If the sizes are given in somewhere you can find it, then it is very easy for you to compare. But for the time being, to understand the rule, I have just assumed the size of magnesium ion and ferrous ion to be same. And you can see very clearly that the charges are same. Now what is the electronic configuration of magnesium? It's 1s2, 2s2, 2p6, 3s2. So to acquire the nearest noble gas configuration, it will lose 3s2 electrons and it will have the electronic configuration 1s2, 2s2, 2p6, which is typical of noble gas. So you can see S block elements, when they form ion, they have this configuration ns2 and p6. And here you can see very clearly, if I assume that n to be 2, so here we have 2s2, 2p6, that is ns2 and p6 configuration. Now look at the electronic configuration of iron. It's 1s2, 2s2, 2p6. For your convenience, I'm reminding you, iron has atomic number 26. So it is 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, 4s2. But actually when you apply Aufbau principle, you know that 4s orbitals are filled up first, then the electron go to 3d. But for your convenience, to understand the ions formed easily, I have written 3d6, 4s2. If you write during exam this way also, you will not get wrong. Now when electron will be lost, 2 electrons will be lost from ferrous. Electron will not be lost from 3d, it will be lost from 4s because this is the last shell. I tell you, quite often the electronic configuration of ions are also asked, and in that case you need to be careful. The way they filled up and the way they lose electron may not be same. Okay, so here we have 1s2, 2s2, 2p6, 3s2, 3p6 and 3d6 and 4s0, which is typical of transition metals or d block elements. You can see here I have marked here the d block elements will have the general configuration n-1 d 1 to 10, ns0. And if you compare here the electronic configuration of iron, what do you notice? You can notice here this part, just concentrate, 3d6 4s0. Now third shell is the second last shell, that's why you have labeled it as n-1, and fourth shell is the last shell, so it is ns0. Now how many electrons in the d orbital here? We have 6, so it is n-1 d6 ns0. Now we have assumed that magnesium ion and ferrous ion, they have same size, and it's very evident from here that magnesium and ferrous have same charge as well. But since iron belong to d block, ferrous chloride is going to be more covalent than magnesium chloride according to Fajan's rule. So these are the 3 set of rules which we learn from Fajan's, and that's all about Fajan's rule. And during exam, I don't expect that they will ask you to write the rules, but mostly they will be asking you set of examples will be given, and you have to identify which one is going to be more covalent in nature. Next is Vsepr theory. I'm not going to discuss in detail of this right now. You can go through the points, they're pretty easy to understand, but just let's analyze the name. You see the abbreviation Vsepr. How do you get the abbreviation Vsepr? We get valence, V for valence, S for shell, E for electron, P for pair, R for repulsion. So it is valence, shell, electron, pair, repulsion theory. Now if we just analyze the name, we can understand what it is telling us. If we analyze the name, you can see the electron pairs rather, I won't say electrons, the electron pairs which belong to the valence shell of an atom, they suffer repulsion. And due to this repulsion, they move away from each other. And they will occupy such a position where the repulsion is minimum. And let me tell you, this is the first theory which more or less successfully could explain the shapes of covalent compounds. Remember the drawback of Lewis concept? Lewis could not explain the shapes of molecules. And this Vsepr theory is the first attempt to understand the shapes of molecules. Now, as you know, we have in the last shell, in the molecules, we may have lone pairs also, bond pairs also. Now, this theory says that the lone pair repulsion, if there are 2 lone pairs, they will cause maximum repulsion compared to if we have a lone pair and a bond pair, and the minimum repulsion will be between bond pair and bond pair. So we'll do the table, we'll try to understand what does this rule mean, and we please go through the points. There are 1 2 3 4 5 6 points in the in your note which I have already sent you. It is there in the book also. So we'll do the remaining part tomorrow. So for the timing, you please do this.